Good afternoon, everybody. Good morning, good evening, since people are joining from various things. I very warmly welcome you to this our webinar of desalination. This is the first time Tec WABAG is organizing a webinar, which is going to be more of a knowledge sharing session by our expert, the Chief Technology Officer, Desalination, Mr. Syed Amir Basha. Mr. Basha is a mechanical engineer with honors from India and has over 4 decades of experience. Out of that, more than 3 decades of experience has been in Middle East and in the desalination sector. He has worked for leading organizations like SWCC Saudi Arabia, Bushnag Group, and for last almost a decade, he has been working with WABAG. He will be talking extensively about desalination technologies, what are the various options available, and how desalination is gradually becoming more viable, reliable, and affordable in the current scenario to ensure water securities, especially in the coastal regions. Just to give a very small introduction about Tec WABAG Limited. WABAG is one of the market leader in desalination technologies. WABAG has built over 60 plants in 17 countries across the globe and is currently desalinating around 1.2 million meter cube of seawater every day. So because of the vast experience of WABAG in various kinds of technology, whether it is SWRO, MED, MSF, TVC, everywhere WABAG has credentials, and all that cumulative knowledge of several decades is something which we are trying to compress given the time constraint over the next 45 minutes to 1 hour. Now in this particular thing, I think if you have any queries, any questions, you can keep on putting them in our chat box, and by the time we finish this thing, where we will have a question and answer session where Mr. Amir Basha will like to reply to as many queries as possible, given the time constraint. So I'm sure that you all will enjoy this session. It is going to be a very, very lively, enriching session. And we all know that desalination is something which is going to grow by leaps and bounds. I'm sure it will add a lot of knowledge to your own. With that, I would request our Chief Technology Officer, Desalination, Mr. Amir Basha, to take over and take us through the next 45-minute session on desalination technologies, which can be the most appropriate in the given environment. Thank you. Over to you, Mr. Amir Basha. Thank you.
Good morning, good afternoon, and good evening to all our joinees for this webinar in various zones. It's my great pleasure to share the knowledge what I have gained in this 4 decade to the people over here so that they can get benefited. And WABAG has built so many plants in the last few decades of its operation, in which there are thermal desalination plants, reverse osmosis plants, and wastewater treatment plants and industrial water treatment plants. Since the time given for me is 45 minutes to 1 hour, I'll be concentrating mostly on seawater desalination by reverse osmosis in this session. Maybe in the subsequent sessions to come, we will cover thermal desalination and other areas also. Okay, many people will be very familiar with the seawater reverse osmosis plant. For the benefit of all who are joining for this webinar, I would like to mention that there are 5 major systems in this any desalination plant, and they are intake system, the function of which is to bring the seawater from the source to the plant area, the pre-treatment system, which treats this water and makes it suitable for its admission into the seawater reverse osmosis system, because there is some stipulated conditions given by the membrane manufacturer for its safe operation, and we have to meet those conditions. So the pre-treatment main function is to make the water that is from the intake suitable for admission into seawater reverse osmosis system. The third system is a reverse osmosis system, which consists of membrane trains, high pressure pumps, energy recovery devices, and the associated control system. Then the fourth system is the post-treatment system or remineralisation system, where we condition the water permeate that is coming out of the RO plant suitable to be distributed to the industrial application or for domestic application or municipal application. And the fifth system is the outfall system, where the brine along with the waste from the plants is dispersed into the sea within a short zone, so that it does not affect the marine organism living in that area. Intake also should be designed carefully so that it does not affect or does not pull any marine organism towards the plant area. So let us start right from the beginning of intake. Intake, there are different types of intakes available. Open intake, passive intake with the compressed air backflushing arrangement, seabed filter galleries, then horizontal drilled direct well intakes, lagoon intakes, vertical vent intakes, and horizontal Rene type intake wells. The one you see here is a large open intake with the velocity cap arrangement. What you see on the left side bottom corner is the velocity head of an 110 MLD desalination plant. If you want to know the size, it is approximately 6 meters in diameter and the height is around 1.5 meters. So the area is so large enough so that the water that is drawn, which is around 10,500 meter cube, it also per hour that enters at a very low velocity in the range of 0.3 to 0.4 meters per second, so that marine organisms are not pulled. So this intake is the velocity head is above the seabed, so it is susceptible for any variation in the seawater conditions immediately, and it has a disadvantage that any TSS carried out in this water will be immediately felt in the plant. All any algae that is brought into that area will be or oil that is spilled over that area will go immediately into the plant area. So for this type of intake or most of the intakes, we may have to do a detailed study about the seawater quality in that zone or area, so that the water that is entering is of a good quality, and because of that the pre-treatment system requirement can be not an elaborate one. A simple pre-treatment system will be able to meet the requirements of the membranes. If the intake is not rightly selected, you will end up in going in for an elaborate pre-treatment system and consuming a lot of chemicals and passing on passing on and increasing the cost of the operating of the unit, that is OPEX costs will go high. So in this this advantage of this thing is it is easy to lay, and also it can be dredged and built very fast. But only a disadvantage, and it's another advantage is that it can be suitable for very high capacity units. Only thing is it is very sensitive for change in seawater quality, and it can be immediately felt in the plant. The next intake is the passive intake. This intake is similar to the open intake. It is also called an open intake, but it is passive because you can allow backwash air so that the inlet can be, whatever that is settled in the inlet can be cleaned. You can see on the right side, this is a intake that is designed for our Algubra 191 MLD plant, which is located in Algubra in Oman. And this has got a wedge wire design, and the gap between the wires is only 0.4 millimeters. So advantage of this is any big particles, everything will be stopped at the mesh itself, and the water that is going inside will have particles less than only 0.4 millimeter. So, but the disadvantage of that is algae growth can be possible. It can get blocked very easily. So you may have to send frequently the divers in order to clean it if your air blowing backwash system is not operating properly. Also, chlorination is very important in this to avoid the growth of algae that can block the wedge wire openings. This also is suitable for high capacity plants. You can have multiple such header arrangements in order to admit water. You can see on the right side that there is an opening where it's a manhole through which divers can go inside and clean the system. This arrangement is a seabed filters gallery arrangement. This arrangement has a big advantage that the sand bed over that galleries which are there will act as a natural filtering medium, and because of that, the water that is coming into the plant will be very clean as filtered through a sand filter arrangement. This arrangement can also have a backwash arrangement, but one thing is this arrangement, if it can be located in a surf zone, the surface can be cleaned by means of the waves that are sweeping through that sand area, and it keeps that the filtering area, surface area clean. If such thing is not there, then we may have to skim through and take the top layer of the sand in order to keep the filtration rate constant. This type of plants are already operating with around up to 50,000 meter cube per day capacity, and this have found to be successful. Only thing what we have to see is the problem associated with the calcination or formation, blocking of the spores, which I will take it up later. This is arrangement of horizontal drilled direct well intake, which is called a neodrain system, and this is specially suitable when your face of the power plant that is having facing the sea is less and you wanted to build a big plant. So this can be like a fan arrangement. You can see this multiple holes are drilled through the seabed and pipes are inserted with serration. The pipe can be as big as 300 millimeter, and the hole that is drilled is 350 millimeters. So the valve, since it is around 2 to 3 meters below the seabed level, the water that is entering into this pipe will be through the filtered bed, and it can, because of that, the water quality that is coming out will be entering the plant will be very, very clean. So your pre-treatment system can be very simple. This is similar to seabed seabed filtration arrangement. Only thing is this is drilled, and there you have to cut a big pit, and where you have to put the galleries, pipe galleries, and over which we have to put a gravel, and then you have to fill with the sand medium. So this arrangement also, and along with that other arrangement which I told about the galleries, has to depend on the permeability of the soil in that zone. If the permeability is good, the capacity will be very good, and if the zone is not permeable, this is you cannot have this arrangement, because the clogging will be very fast and you will not have enough water output from these units. So first thing you have to do for such an arrangement is a detailed study about the seabed and its permeability and whether it is sufficient to give the required yield for the plant for running the seawater desalination. This is a lagoon arrangement where water is brought into a lagoon and it is made to stay there for a longer time before it enters into the zone where intake is, where the pump's house is located. So because of this, the main advantage is that the high TSS in that zone, if there is, it will be able to, it will allow to settle in this lagoon area. And because of that, that is 4 or 5 days volume, storage volume is there, you have enough time for settlement and you can take a clear water from this. I have seen that some of the plants in Gujarat area, when I went, I saw a lot of the TSS in that seawater is very high, and for such area, this lagoon type arrangement is very much preferable. But the lagoon should have an arrangement to isolate, divide it into half, and also desalate it when it is required. So this is one of the requirements for this lagoon type arrangement. And this is also suitable for high capacity plants. The one which you have shown here is the Renish type intake well and a vertical well arrangement. Vertical well arrangement shown on the right is a single beach well arrangement where you can draw water up to 300 to 400 meter cube per hour. It is suitable for smaller application like 2000 or 3000 meter cube per day plant. But the one which is shown on the left side is a horizontal Rene type intake well. This is to increase the area. You can see there are a lot of laterals at the bottom, and the laterals will bring in more area for filtered water to enter and come into the well area. So this is very much suitable for a place where there is a coral base is there, or the permeability of the soil is very good. This is not suitable for a clay type area or silty area, and then there is even backfilling, anything is done in those areas, we cannot have such wells arrangement. And in Malta, this Rene type well arrangements have been used for a capacity up to 56,000 meter cube per day. So I was telling about the pluggage and the cementation of the soil. See, it involves ions carried in the groundwater, and they chemically precipitate to form crystalline material above the grains of the sand, and then the pores are filled by these minerals and they form bridges between the sediment grains, thereby binding them together, and it becomes a sandstones. So this is the main disadvantage in any lateral type arrangement or neo-drain arrangement, or in the Rhine's well or a single bore type wells. So we need to be very careful in analyzing the possibility. In a bore well test and all, you have to do a drawdown test in order to ensure that you get enough water for at least 10 to 15 years for the operation of the respective plant, and they are suitable for a medium or low capacity plants only. Now let us go into the pre-treatment system, and there are many components associated with this bar screen and traveling band screen, dual media filters, or dual media gravity filters, dissolved air flotation system, clarifier or lamella clarifier, disc filters and auto strainers, MF or UF, that is ultrafiltration or microfiltration, and the chemical dosing systems associated with this. So you may use either one or in combination in order to achieve the required quality of water at the RO inlet. Bar screens and traveling band screen. The first one inclined that is shown here is a bar screen. Normally the bars are at a pitch of 20 millimeters and they are just 5 to 6 millimeter thick. The main function of it is to remove any gunny bags or rags that are coming into the plant, and even in the big shells which are coming into that can be stopped at this point, and it can be raked and brought out of the system. So whatever the shells, barnacles which are accumulated along with the rag can be on the bar screens can be racked out and then brought out and disposed. So, and this is followed by a traveling band screen, or we call as a cup screen, whatever it is. These screens have perforations of diameter 2 to 4 millimeters, and the main function of it is to remove particles above 2 to 4 millimeters, so that even the barnacles are not allowed to pass through the system. And this forms an essential system in case of open intake system, as well as in the passive screen system. But in other systems also, I have found that if this is available, it is preferable, in the sense actually there will be a lot of growth of mussels, shell shells and barnacles into the intake or intake pipe. When you do shock chlorination, these are carried into the intake system sump. If you don't have these systems, this bar screen as well as traveling band screen, those shells, they directly go into the intake pump, and they are picked up or sucked by the intake pump through their strainers. The strainers generally have an opening of around 15 to 20 millimeters, and they are crushed, and then they are made to flow downstream along with the water. This, when it passes through microfiltration or an ultrafiltration, they can damage the fibers and they can force you to plug the fibers. So in such systems, it is preferable to have the traveling band screen. At least, if not bar screen, at least traveling band screen is essential in order to protect MF and UF, where the bio growth and especially the shells and barnacle growth is very high in the intake system, because when you shock chlorinate it, it is carried to the pump sump. This is a dual media filter. The arrangement which is shown here is in 195 MLD Algubra plant. We have 52 such big dual media filters. Dual media filters has got anthracite and sand with a nozzle base at the bottom. So water flows into the top and then filtered through the anthracite and sand and comes to the bottom, gets collected in the nozzle arrangement through the header. It is taken into the plant area. So in the process, this gets the bigger particles get collected here due to the more bigger voids in the anthracite, and smaller particles are getting collected here. So this has a filtration duration of around 24 hours. So once in 24 hours, it is backwashed by admitting filtered water from the bottom through the nozzles. Fluidization of the this media takes place, and that releases the entrapped particles, which is carried out through the outlet pipe, and then it is taken out and dumped outside as a backwash water. So this system is very simple, and when your intake is quite good, the water quality is good, it is preferable to go for this system, because the capex is also low and opex is also low, and very easy to operate, very simple to maintain. And where slightly more particle collections are there, it is better to go in with the air scoring to break the first the cake, that formations, and then do the backwash following the air scoring. So this is very commonly seen in a simple desalination plants. This is a gravity media filter. There, the one which we saw previously is a pressure type filter, where the pressure is used around from 1.5 to 4.5 bars, depending upon the system requirements. Whereas this is a gravity filter where the hydraulic head of water that is accumulated over the media acts as the driving force for the water to filter. So this has a lower filtration rate when compared to the pressure filters which is seen previously. So by using a special media in the pressure filters, you can go up to a filtration velocity of up to 15 meters per hour, whereas normally the gravity filters, even if it's a rapid filter, we go up to 10 meters per hour as the filtration rate. This also similarly, you have a filtration cycle followed by a backwash cycle in order to clean it. And normally the backwash cycle takes place every 24 hours to rejuvenate the media and make it ready for the next filtration cycle. So you can see the nozzle floor is at the bottom and 2 layers of media are on the top, and the water distribution is through raw water inlet. And the backwash takes place through the collection trenches, and it is disposed out. Dissolved air flotation system is becoming more and more common because of recent bloom in the algae and also red tides, which are often seen. Most of the plants recently getting built in the Arabian Sea area in the Middle East are built with the dissolved air flotation system. In the dissolved air flotation system, water enters and it is coagulated and mixed in the mixing chamber, and then it is admitted into the flotation tank where saturated air water is admitted from the bottom and these micro bubbles are formed and when the saturated air and water is released through this header, and these fine bubbles lift the light particles and takes it to the top. So algae, oil particles and are just lifted up and they stay as a scum, and they are removed by means of skimmed off, and then it is removed out. So the main advantage is any particles which are light can be easily removed in this process. Also, this there has an advantage of bringing down the TOC level by proper coagulation in this arrangement. So with this arrangement, if you are incorporating, you can have a bypass arrangement so that when there is no red tide or algae, you can bypass and reduce the power consumption in the dissolved air flotation system. But we have seen that if you miss it during the initial stage, then incorporating it, because it requires a lot of area and additional design features, which makes it more costlier. So it is very essential, I repeat once again, that the seawater analysis for at least 1 or 2 year period is essential in order to decide the right pre-treatment system. This is a lamella clarifier, or another type of clarifier which can be used is a normal clarifier, which is round. And this lamella clarifier, we have once again a coagulation done in the mixing chamber, and then it is the water with the coagulant is brought into the flocculation area, where the flocculators spin at a very, very low speed of around 1.6 RPM to 2 RPM, and they agglomerate the particles. The particle that is agglomerated along with the seawater enters into the lamella chamber, where plates are kept inclined to increase the surface area for settlement. So the water normally enters from the bottom, and then it rises slowly from the bottom through these gaps in between the parallel plates, which are kept at 60 degree and above. So when it is rises, you can see in the right side, the particles through the gap, it tries to settle down into the plate area and then slips down to the bottom and falls into the hopper area. From the hopper area, it is evacuated as a sludge. So you can see this is the pack of plates which are kept, which can also be used instead of inclined plates. We call it as a tube settlers. So the main advantage of this is I have operated lamella clarifiers during cyclones when the TSS goes even up to 1,500 milligrams per liter. we were able to settle down all the TSS, total suspended particles, and able to remove. Only thing is we are forced to evacuate the sludge instead of every 12 hours or 24 hours. We had to evacuate it once in 3 hours or 4 hours. Otherwise, the hoppers are getting filled very fast. So even with the inlet TSS of around 1500 milligrams per liter, we were able to get a clean water with less than 20 milligrams per liter of TSS. So this is very effective. So if your TSS levels are high, please, you can go in for lamella clarifier, which is very compact. It occupies lesser area when compared to the normal clarifiers, and very, very effective. And the consumption of coagulant is also not much high in lamella clarifiers. Then comes the more advanced UF ultrafiltration system and microfiltration systems. And the one what you see on the left side top is the Pentair's ultrafiltration system in the 110 MLD Nimili desalination plant. And the right side one you are seeing is an Inge ultrafiltration system membranes in one of our, because we have multiple plants with this Inge arrangement. It is one of our plant which has the Inge ultrafiltration system. So whenever you have an ultrafiltration system or microfiltration system, you have to have either a disc filter or auto strainer in order to remove particles which are above like 100 to 150 microns, so that the membrane system is not overloaded. So the one what you see in the left is a disc filter which has got multiple discs arranged in one arrangement, and the serrations at each disc gives the required pore size, like 100 microns or 105 microns. So the water flows from outside to inside, so all the particles which are higher in size get settled outside, and then there is a filtration duration of either 60 minutes or 75 minutes, depending upon the filtration particles which are there which in the system. And once that cycle is over, you allow the water in the reverse direction to backwash and get it cleaned for the next cycle of operation. So if you see, the number of disc filters generally when compared to auto strainers are much higher. For example, in a 110 MLD plant, we have around 120 disc filters, whereas auto strainers you can manage with 5 to 6 auto strainers, a big size. In auto strainers, you have a strainer and the water particles, enter and pass through the strainer, leaving the TSS on the surface of the strainer, and this is automatically backwashed continuously and it is removed out. So you can either go in for an auto strainer or a disc filter prior to UF or MF, so that the life of UF and MF can be improved. The one what you see here in the center is a sectional view of a ultrafiltration system with fibers which are hollow in nature. So you can have it an outside in type or inside out type of a filter, and there are different makes available in the market. Different chemical dosings are used in the pre-treatment system. One is important is either shock chlorination or continuous chlorination. You have to judicially decide about the shock chlorination or the normal chlorination depending upon the nutrients level which is available in the seawater. So you cannot follow a thumb rule to use it and then for every plant. So it depends on plant to plant, it varies, and it depends on the nutrient level available in the seawater. Then acid dosing is to be done if required to adjust the pH in order to enhance coagulation and flocculations. And then dechlorination is a must when we use chlorination, because most of the membranes what we use are non-chlorine tolerant membranes. In order to save the membranes, you have to go in for dechlorination. Modern plants use higher recovery rate. and recovery rate in the sense that if you admit 100 liters of water and take out 40 liters of pure low salinity water, then it is 40% recovery. So modern plants are built with a recovery of even 45 to 50%. And so the scaling tendency in the membranes will be higher when it comes to the brine side. So in order to avoid scaling, the programs are available to run and select the anti-scalant and the dosing rate. So anti-scalants are used in order to increase the recovery rate in the plant. So without increasing the infrastructure, by proper selection of anti-scalant, you can go for slightly higher production. Then when come for the RO design, we have conventional design, we have inline design, we have a pressure-centered design, and the membrane selection possibilities are there, and an energy recovery device selection possibilities are there. In the conventional design, you have pre-treatment system. It comes through the disc filter, then goes to the ultrafiltration tank, and then the pre-treated water gets collected into the UF product tank or intermediate storage tank. From there, separate pumps pump the water to the RO units. So in this system, there is a tank in between. So it divides the pre-treatment system and RO system so that even pre-treatment system can be designed to operate independently and RO system can be tried to operate independently. By doing so, what happens now, even when a pre-treatment system trips for a few seconds or few minutes, RO system can keep continuously running. You can start back the pre-treatment system and join. The only concern in this is you need a bigger tank area, and where there is an area constraint, people now try to go in for non-conventional system, which is an inline system. And this type of system we have adapted, and it's successfully operating in 110 MLD Nimili desalination plant. And this plant is operating for last 8 years, and we are running almost at a full capacity. This is inline system, which we have designed in our Algubra plant. In inline system, we avoid that intermediate tank. So from water, when it enters the pre-treatment area and it comes out as a permeate and from the RO system in one stream completely. So in this system, there is no intermediate tank. And because of that, your control system tuning should be perfect so that any disturbance in the pre-treatment system should not trip the RO plant. So in order to that, you have to have more instrumentations, and also you have to have a proper tuning during commissioning in order to have the success of this. The main advantages of this system is it reduces the tank area. Because of the tank is eliminated, slightly power consumption saving is also there, because whenever there is a tank is there, you lose some energy in it. You pump water and lose the energy. So that gain is advantage in the inline system. So you can have slightly reduced specific power consumption in these plants. This is pressure-centered design. In the pressure-centered design, we have a unique arrangement where the high pressure pumps are common, energy recovery device is common. So because of that, even you have a 200 or 300 MLD plant, you will have less number of high pressure pumps, less number of energy recovery device and booster pumps. In the previous two arrangement, conventional arrangement and the inline arrangement, you have individual train, separate high pressure pump, separate energy recovery device, and separate booster pump. So the advantage in this central pressure center design is that you have a bigger system. Because of that, efficiency is higher. But the main disadvantage is there are a lot of common headers. Because of the size of the quantity of water that is handled is high, these headers are quite big, and especially when there's a high pressure headers, the thickness is high and it becomes slightly expensive. Also, any leakage in the common pressure system will result in stopping the complete plant in order to repair it. So your quality control in the welding process and proper welding should be given more importance in this pressure center system. So there is some advantage in space saving also in this design. Now we come to RO membranes. There are most of you will be familiar with this spiral wound membranes. So the configuration of the spiral membrane is the membrane sheets are wound in the form of a spiral and made cylindrical and made in the standard length of 8" by 40" or 16" by 40". They are standard available, and for higher capacity plants they go in for 16", and for smaller capacity plant they go in for 8" membranes. This is a sectional view of a spiral wound membrane flat sheet. You can see that this is the real polyester base which gives the strength for the membrane sheet. This is one sheet which is shown as a section here. So the polysulfone layer is also a supporting layer. Real membrane layer is the polyamide layer, which is a very thin layer in few angstrom units. So even small scratch can damage this layer. So you should be very, very careful. And this polyamide layer, if it is damaged, then your salt passage through the membranes will increase. So while handling the membrane, or pre-treatment should be done properly in order to avoid this polyamide layer also damaging. And when you do frequent CIP also, the polyamide layer get deteriorated and the salt passage increases. The other type of membrane, what I just want to bring to your knowledge, most of the people will not be knowing, this type of membranes are mostly operating in Saudi Arabia or in Japan. They are called hollow fine membranes. There were two types of hollow fine membranes which were available. One is made by DuPont, another one is made by Toyobo. So DuPont stopped its production maybe around 10 to 12 years back, and now it's no more available as a hollow fine membrane, but now they are making now spiral wound membranes. But these hollow fine membranes, they are made up of cellulose triacetate, and this membrane has a special advantage that they are chlorine tolerant membranes, whereas all polyamide membranes or spiral wound membranes are chlorine non-tolerant membranes. So any feed water with slight biofouling can be used with this with an intermediate chlorine. And you can see the sectional view of the arrangement which is on the right side. You can see that it's a tube-like structure. It's a very fine fibers which are arranged inside. So the area available is very high, and because of it, the skid arrangement is very compact. Another main advantage is of cellulose triacetate is they operate at a higher pressure around 80 bars. But the quality of water you get as a permeate is excellent quality. I have seen plant operating with the feed TDS of around 41,000 ppm, and the outlet quality of water is 160 to 180 microsiemens or 80 to 100 maximum milligrams per liter of permeate flow. So in singles, actually single pass, you will be able to get the high quality water which is suitable for domestic or applications completely. And here also we have 8" and 10" membrane. Two sizes are available. In spiral wound we have 8" and 16" membranes, and large units they go in for 16" membrane in order to reduce the fittings and reduce the footprint area of the plant. Energy recovery devices. You can see the progress we made in the energy recovery devices starting from 1980, where we started Francis turbines. Then we had belt and wheel turbine arrangements, then hydro turbochargers, and currently the two energy recovery devices which are famous are Calder's Dweeb type and ERI's pressure exchangers. These two are very, very, very popular now because of its very high efficiency in the range of 97 to 98%. Hydro turbochargers were more suitable for smaller units with the less capex requirement because they are easy to install and they have an efficiency in the range of 85 to 86%. So these pressure exchangers or work exchanger came in this 2001 and 2002, and they became very popular, and almost all the units currently being built are with these two type of pressure exchangers and energy work exchangers. The one what you see here in the left is the work exchanger, and this work exchanger, you have multiple cylinders. In these cylinders, there is a piston arrangement where the low pressure water comes in one end and the high pressure water comes in the other end, pushes and transfers the energy. So this arrangement has a valve in order to intake high pressure water and release the low pressure water. So this is generally made up of super duplex stainless steel. So there is slight possibility of corrosion is there, and involvement of valve maintenance is also there. This is on the right side. It is a pressure exchanger. It is smaller in size, and number of units required are very high when compared to Dewey's Calder units. And in this pressure exchanger, the inner rotor part is completely ceramic, so it is it doesn't have you need not worry about the corrosion due to seawater. Also, there is no bearings are involved, even though there is a rotary part used. Seawater is used as a hydrodynamic bearing, and because of that, no bearing is required inside system. So it is pure ceramic, and it takes all the wear and tear for even a long time. You can see that this pressure exchanger is located in the brine system. So the brine water comes in, and it does not have any valves. It enters the port, and when the water at low pressure enters from the other end and pushes to the other end, and by the time it comes to the other end, the rotor changes its position and comes to the discharge port opening. So since we lose around 1.5 bar or 1 bar in the membranes and another 0.5 bar in the recovery device, the losses have to be made up by means of the circulation pump, so that the pressure at the point of joining between the high pressure pump and the circulating pump is same. So this makes it very attractive that the high pressure pump energy required is only equivalent to the permeate conversion rate. That is, if this is a 40% recovery unit, only 40% of the water is pumped through the high pressure pump. Remaining 60% is through the energy recovery device. So it gets the energy from the brine. So both Calder and ERI work on the same principle. So because of that, the energy saving is huge, and the energy recovery is 98% in these two units. So this made the specific power consumption of the RO plants to come down drastically, and nowadays we are able to operate the plants in the range of 3 to 3.5 kilowatt hour per meter cube. Then the post-treatment or remineralization comes in, where we do the pH adjustment. Also, we have to do LSI adjustment. LSI is longilinear saturation index, and it is generally done with the addition of calcium and R by adding sodium to it. If you see in pH adjustment by limestone filter and CO2, we pass through a limestone filter in order to pick up the calcium. In the other arrangement of saturated lime water, actually you prepare a slurry and then pass through a clarifier and to get lime milk, and then that is used in order to increase the pH level. In smaller plants, where they use lime powder and CO2 directly, but this has a disadvantage that lime powder can settle down, and in due course of time it can block the pipeline. So you have to have a detachable pipeline arrangement in the post-treatment so that it can be removed and replaced with a new one. So this is just adapted only in a smaller units. pH adjustment with sodium hydroxide can also be done without any lime or CO2, but this addition is suitable for only smaller units because it slightly changes the taste when the pH level goes above 8.5. And there are some special additions like fluoride addition in the drinking water plants, the domestic units of Aramco and all, they use calcium fluoride in order to add fluoride to the drinking water, so that enough fluoride is available for the teeth, which is very rare. Also, there are some plants which can add some flavor to the potable water that is coming out, and by means of a special additives. So this is as per your requirement, we can do it. This is the schematic arrangement of a limestone filter. You can see that carbon dioxide is injected into the carbon dioxide absorption to mix the carbon dioxide, and carbonic acid along with the water enters into the limestone filter. When it flows from top to bottom, it picks up the calcium from the limestone, and then the water is passed through the degasifier and then admitted into the potable tank. So you can see that in this arrangement, 70% of the water can be directly taken to the tank. Only 30% has to be allowed through it to pick up the calcium, and final mixing can take place in the potable water tank to give the required pH level as well as the LSI positive. You can see these are the lime filters in our 110 megawatt, 110 MLD desalination plant, which is at Nimili, and this is the degasifier unit, and this is the underground tank. So this arrangement is very simple, and it is easy to operate. And the charging of limestone takes place through means of ejector arrangement, and once in a week charging is more than sufficient in order to maintain the required pH and LSI. The second arrangement where saturated lime water addition is there, actually water is taken and a slurry of lime is brought into this lamella, and there a saturated lime milk is created, and this is injected along with the CO2 in order to create the required pH and LSI. So a sectional view arrangement of a lamella is given here. The main function of a lamella in order to make a concentrated saturated lime milk solution in this arrangement. The final one, what we are going to see is a disposal through of our brine and the waste in the plant. It can be, main thing is olden days we were disposing it directly to the shore, which is no more allowed. So it has to be taken deeper into the ocean, and it has to be dispersed within a short zone so that the marine organisms are not affected. So you can do it through a pipe diffuser. Then it can be also done through a venturi diffuser. It can be disposed through ocean floor discharge, which is similar to the laterals which are there for intake. Similar arrangement can be made in the outfall, and then we can discharge this water through the gravel so that it comes out distributed and diluted within a short range. And then there is a disposal arrangement, mixing through cooling water if it is near a power plant, where the cooling water quantity will be very high, so the brine is diluted and get dispersed. And then it can be also from the mixed along with the treated wastewater and can be disposed into the sea. This is the arrangement about a diffuser arrangement which is used in Nimili desalination plant. It is a 40 meter long and 1.2 meter diameter diffuser with multiple nozzle arrangement and with a recirculation. So this diffuser we are able to disperse, and within a 30 meter radius we have measured that the brine concentration comes down, and the difference between the seawater and the brine is only 3% in the 30 meter radius. This is a diffuser, a venturi type diffuser arrangement, where you can see that water enters directly and it is discharged, but when it passes through a venturi, it creates a suction, and the outside water also enters and mixes, and then brine is diluted when it comes out. So you can have a multiple venturi diffusers in order to diffuse that water. Thanks. Last slide.
Thank you so much, Mr. Amir Basha, for giving us this enriching session on desalination. I'm sure all the joinees who are there, they would have benefited from it. With this, we would like to, for next 10 minutes in the interest of the time, we would like to, open it up for question and answer session. So all the questions, you can put it into the chat box and we'll be more than happy to answer that. So we'll start with one question which has come from Mr. Radhesham Tyagi. What is the percentage of remediation, which is the what is the unit cost of treatment?
See, I can tell about the price, international price as on today for the seawater desalination has come down in a boot plant to $0.43. So it is becoming more and more competitive. It depends on various factors like power cost, which forms around 60 to 70% of the total water cost, that is unit water cost produced. Also the labor charges and chemical costs in that area. So it zone to zone, it is different, but in the Middle East area, it has come down to $0.43 per meter cube.
There's another question from Mr. Muhammad Akbar. We understand that the gallery style of intake system is more applicable for river water application. Do you feel that it is applicable for seawater applications also?
Yes, it is very much applicable. It is being tried in at least 4 or 5 plants, and these plants are operating. And these are not small plants. There are plants of capacity up to 50,000 meter cube per day are there operating with the galleries in the zone.
Thank you. There's another question from Mr. Anand Raj. What are the disposal methods of sludge which are removed during the pre-treatment?
Yeah, actually sludge concentration is done and it is passed through the centrifuge, and by passing through the centrifuge, you are able to increase the sludge consistency and remove it almost and dispose it through trucks.
Thank you. The next question is from Mr. Sushil Kumar. In fact, there are 2 questions. The number one, what is the overall efficiency of the entire system in terms of output versus intake water output?
Right. It is generally, if you can consider that if 100 liters of water is taken, we are able to convert in a Nimili plant. We are converting up to 40%. So I can say that the recovery rate, overall recovery rate from a point of the permeate, that is our potable water produced, to the water that is taken from the sea is 40%.
The next question is there any desalination process where no chemicals are used in the process?
Yes, there are some few plants where there is no chemicals are being used. It all depends on the quality of seawater. If your seawater is very clean, and suppose if it is drawn from a beach well, the probability of using chemicals is very, very, very less. We don't use pre-treatment chemicals, but anyhow, for chemical cleaning, at least once in a year, you have to do CIP of the membranes in order to have the surface to be free from any particle settlements or any mild scale formations and other things. So membrane manufacturers recommend at least once or twice a CIP of chemicals, even though there is no scaling or fouling there in the membrane.
Thank you, Mr. Amir. The next question is from Mr. Sultan Ahmed. In which plant the lamellar clarifiers are used?
The plant which I am operating, which is 110 MLD Nimili desalination plant, uses lamellar clarifier. And I told you that we operated even during the cyclone, and we operated with the TSS of around 1000 490 milligrams per liter, and we got a lamella clarifier outlet with the 20 milligrams per liter of TSS, and the plant operated during the entire cyclone process also.
Next question is from Mr. Madhman. What is the approximate cost of desalinated water through SWRO in large capacity plants?
See, in last 10 years, the wood plant water cost internationally has come down from around $0.6 to $0.43. This is international wood plant prices, where the capacity of the plant is about 300,000 meter cube per day, or 300 MLD.
The next question is again from Mr. Radhesham Tyagi. As you know that Delhi is facing water crisis despite of the fact that groundwater is in abundance in Najafgarh stream and right from Palla to Wazirabad, but it cannot be utilized due to high salinity. What is the potential of reclaiming of drinking water from this stream? How the brine can be disposed of? What would be the unit cost of treatment? What percentage of water can be reclaimed from this source? The TDS varies from 2,000 to 3,500. I think there are too many questions.
Yeah, I can answer it. I can say that a brackish water plant can be installed in order to treat this water and produce drinking water. We can go up to 75 to 85% depending upon the chemical constituents in this water. So 85% recovery can be possible. Brine disposal can be done either by means of evaporation pond or by means of injecting into the wells, deep wells. That's possible. Or if there is any possible seashore or something nearby, we can dispose it there. But since you are telling Delhi, you have to have an evaporation plant. In Saudi Arabia, there are evaporation ponds for plants up to 1,200. 120 MLD plants have evaporation ponds in order to dispose the brine.
Thank you. The next question is from Mr. Nitin N. What is the criteria for choosing between lamella clarifier and DAF?
Lamella clarifier is for total suspended solids, whereas DAF is for light particles like algae and TOC reduction, as well as oil traces what are there. So they have two different functions and they work on two different principles. One is settlement principle, another one is lifting it due to the air and then skimming it off. So they are work on almost opposite principles.
The next question is from Mr. Balasubramanian. Considering the UF membrane cost and high maintenance involved in UF system, can we avoid UF system and focus on RO system and all?
Yeah, the necessity for UF system depends on the seawater quality. If your seawater quality is good, you can go ahead with the dual media filter itself or gravity filter itself. There are many plants running in the world with the just gravity filter or dual media filters. But however, I have also operated a plant with the beach well, just only with a cartridge filter. There is no other filter there in the system. So it all depends on the feed water quality, what you get for the as a raw water for the system.
The next question is from Mr. Anil Rai. What is the importance of a pilot plant for a large scale SWR projects?
Pilot plants are definitely useful for a large capacity seawater reverse osmosis plant to optimize the design. For example, dual media filters, if you want to select, you can go for a pilot and go in for high flux that is possible in that, and so you can optimize the design. Similarly, MF, UF and RO combination can also be run as a integrated membrane system. And then you can have what is the CIP rates, what is the cleaning frequency to be used, many things, advantages. For example, in the first UF plant which is built in Saudi Arabia, they had a pilot plant operated for 2 years in order to establish the parameters with which it can be operated. So it was a grand success right from the beginning itself. So your mistakes are minimized and optimization design is high with respect to pilot plant operation.
Thank you, Mr. Amir. I think as we have already exceeded our time, we will take last 2-3 questions now.
Okay.
So the next question is from Mr. Sushil Biharudas. Can you update about the various types of chemicals used in the plant in SWRO? Any research ongoing for alternative chemical use in SWRO plants that is environmentally sustainable and low cost treatment, post-treatment, seawater and wastewater treatment?
Yeah, a lot of chemicals are used. For example, sodium hypochlorite is used for so hydrochloric acid is used. Antiscalant proprietary chemicals are there from different suppliers, and you have also sodium bisulfate to neutralize the chemicals. This is the process chemicals we use. We use lime and sodium hypochlorite for remineralization and post-treatment process. Whereas in CIP, that is chemical cleaning, you use citric acid at low pH, or we use EDTA along with along with the adjustment of pH in order to clean it. This is one is low pH cleaning, other one is high pH cleaning, and whatever the chemicals which are used are neutralized before discharging into the sea. So there's no need to be afraid about the chemicals being used. Except the antiscalant portion, all the other chemicals are neutralized.
The next question is from Mr. Mohammed Sohail. Typically, SWRO operates with a pressure of 60 to 80 bar. Is there any technologies working in which we will have membrane that could maintain salt rejection efficiently with 20% to 30% less pressure? That is up to 50 bar.
Lot of research is going into the membranes. Like nano membranes are being developed. Carbon nanofibers are being developed. Also, there are many other developments are going on. Even membrane distillation process uses only 2 bar pressure. Forward osmosis pressure also uses a lower pressure. But these are in the infant stage of testing, and prototypes of smaller capacity are being built and operated. But anyhow, today, seawater reverse osmosis is the standalone process which is cheapest and which can go for a high capacity like the 300 or 400,000 meter cube per day. Yes, maybe another 5 years you will have membranes with operating with lesser pressure than 50 bar and specific power consumption less than maybe 2 kilowatt hour per meter cube.
So one last question from Tom Zhang. Is the cost of 0.4 USD per cubic meter for desalination treatment?
Yes, it is for the seawater reverse osmosis plant. It is for the recent plant which is floated in Saudi Arabia. This is the price 0.43 up to 4.6. These are the two prices got for two recent plants.
Okay, next. Okay, one more last question from Mohammed Farooq Khan. How are the pre-treatment equipment, including DMF, piping walls, etc., are protected from seawater IPDs? Is a rubber lining or duplex SS only solution available?
Both are being used in practice, but super duplex stainless steel, when it is used, you can be rest assured that you need not open the valve for another 4 or 5 years. But if it's a rubber lining is used, whenever during installation, if there is any pinching is done on the rubber lining, then immediately the valve fails because it blows up, and due to water entering into the stem and the other area, disc area, it corrodes and the lining material comes out. So if you want to have a trouble-free operation for 10-15 years, you can straight away go in for super duplex stainless steel, but it's very expensive.
I think as many questions as we could accommodate, we have already accommodated. If there are any questions which are there in our chat box which are unanswered, we would definitely, write back to you. You can write to us, and we will definitely reply to all your questions through our expert, Mr. Amir Basha. With that, I would like to conclude this particular webinar and like to thank each and every attendee who has taken out this time, and I'm sure you would have enrich your knowledge on the desalination technology. In case you want any further information on desalination technologies, please do write to us. We'll be more happy to organize future sessions with Mr. Amir Basha. With that, once again, a big thank you to each one of you for sparing your time to listen to Mr. Amir Basha. Thank you.
Patient listening. Bye.